Hello everyone, and today we are going to discuss the phenomena of pair production. This is basically the conversion of energy into matter. And before discussing the phenomena of pair production, uh, you have already gone through the photoelectric effect, in which a photon of energy h nu strikes an atom or a surface metallic surface and transfer all of its energy. The energy of this photon is h nu, and transfer all of its energy to the electron of an atom, and the electron comes out from the surface of the metal, and this electron is known as the photoelectron. So this phenomena is known as the photoelectric effect, in which the photon transfer all of its energy. Okay, this is photoelectric effect. Second is the Compton effect. Here in the Compton effect, a photon of certain energy h nu scatter with an atom and transfer only part of its energy to the electron of the system, and the electron comes out from the system, and the rest of the energy and with the rest of the energy the photon goes off scattered with this electron. Because you see that energy is here is h nu prime, here is h nu prime, and here is h nu, so that there is energy difference, and the difference in the energy is taken away by this electron. So in the photoelectric effect, the total energy is transferred to the electron, and in the Compton scattering, the part of the energy transferred to the electron, and with the rest of the energy the photon is scattered away. The third is the pair production. Okay, in the pair production, a photon which is an electromagnetic energy basically is converted into matter. So we have a photon, you see photon here, photon is coming with certain energies h nu, and this is the nucleus, and then photon comes in the vicinity of the nucleus, and then it breaks into an electron and a positron. This is an electron, this is a positron. So the energy h nu materialize into two particles, which is an electron and a positron. So that's why the electromagnetic energy is converted into matter, the conversion of energy into matter, and this process is known as the pair production process. So as we know that in any process there are conservation laws to be hold good, and you know the conservation, energy conservation and momentum conservation, and there is similarly we are going to check here the conservation of charge also. So as you can see that no conservation principle are violated when an electron positron pair is created, when an electron proton pair is created when near an atomic nucleus. This is an important part of this process. So if this nucleus is not there, then there will be violation of conservation principle. We will see it later. So let us first take the conservation of charge. So you can see in the conservation of charge, in the initial you see the charge of the gamma is 0, because this photon is neutral particle initial, and then when it comes and breaks into two particles, so as you know, charge of an electron is -1, charge of a positron is +1. So +1 and -1, final charge is 0. So initially the charge is 0, and finally -1 plus +1 is also 0. So there is a charge conservation. Okay, so you can see that the sum of the charges of the electron, which is -e, and of the positron, which is plus E, is 0, which is as is the charge of the photon. Now let's the energy conservation part. So what experimentally has been observed that the energy of photon, which is gamma, is equal to okay, energy of photon is equal to energy of the electron plus the energy of the positron. Okay, so experimentally, if we measure the energy of the electron and the energy of the positron, they almost I'll say they almost come near to the energy of the photon, and a very less amount of energy is taken care by this nucleus. Okay, because this nucleus is very heavy, so it's not going to absorb more of the energy of the photon, and the rest of the energy, most of the energy, almost equal energy, is distributed into electron and positron. So the total energy including the rest energy, so when I say total energy including rest energy, means because you know already that the total energy for a relativistic particle is equal to kinetic energy, which is p square c square, and this m naught square c4. This is the rest mass energy, and this is 1 by 2. So this is rest mass energy, or say rest energy, and this is your kinetic energy of any particle. Okay, so for example, the rest mass energy of electron, which is this is m naught c square of electron, and similarly m naught c square of positron is 0.51 MeV. MeV is because you know electron volt is the unit of energy, and this is 10 to the power 3 electron volt. So the total energy, which includes the rest energy, because rest mass energy is the energy with which the electron or positron produces, and the kinetic energy with which the electron is moving away from the system. So the kinetic energy plus the rest of energy will be the total energy of the electron, and similar way the total energy of the positron. So the total energy including the rest energy of the electron and positron equals the photon energy. Okay, so the charge conservation is there, and the energy conservation is also there. Now comes the linear momentum, conservation of the linear momentum. Okay, and this linear momentum is conserved with the help of the nucleus. This is important. So that's why the presence of the nucleus is important, because if the nucleus is not present, then there will no be conservation of linear momentum. So this nucleus carries away enough photon momentum for the process to occur. Otherwise this process will not occur. We'll see this statement mathematically in the next slide. And because the relatively enormous mass of the nucleus, the nucleus absorbs only a negligible fraction of the photon energy. So as I already told you that the most of the energy, almost equal energy, is taken care by this electron and positron, and only a very negligible amount of energy of this photon is taken care by the nucleus. So the overall, the energy and linear momentum could not both be conserved in this process of pair production, if it occur in empty space. Okay, so what does mean? The pair production, the phenomena of pair production does not occur here, means in empty space. So if this nucleus is not present in the vicinity of uh, this photon, then this photon is not going to materialize into a positron and electron. So presence of this nucleus is important. So we'll see this in the next slide. So this, you can see here that the race mass energy mc square of an electron, as I have already told you, because the electron volt is mega electron volt is the unit of the energy. So hence the pair production requires a photon energy of at least 1.2 MeV. So what it says that I need at least greater than equal to 1.02 MeV of energy of the photon. Why? Because the mass mc square of an electron is 0.51 MeV, and if I add into the mc rest mass energy of the positron, this is 0.51 MeV, and it sums out to be 1.02 MeV. So if in the final we have a particle which is electron and positron, and the sum of their energy is 1.02 MeV, so in the initial state, the photon must have energy at least equal or greater than 1.02 of MeV. If it's less than 1.02 MeV, then this photon is not going to materialize into electron and a positron. Okay. So in addition, any additional photon energy is the kinetic energy of the electron and the positron. Okay, so if energy is of the photon is greater than 1.02 MeV, so the more energy greater than 1.02 MeV will be distributed to the kinetic energy of the electron and positron, and the corresponding maximum photon wavelength is 1.2 picometer. Okay, so if you calculate the photon wavelength corresponding to this energy, so that will come out to be 1.2 picometer. You know how to calculate it. And electromagnetic wave with such wavelength are called gamma rays. Symbol is gamma, you know already, and are found in nature as one of the emission from the radioactive nuclei and in cosmic rays. So the photon which give rise to the phenomena of pair production must have an energy of at least 1.02 MeV, and of wavelength, corresponding wavelength has to be 1.2 picometer, and such photons are known as the gamma rays, and these are naturally found in the emission of the radioactive nuclei and in the cosmic rays. Now let's move to the mathematical description that to how to show that the pair production cannot occur in empty space. Fine. So here you can see that in this pictorial representation that this is a photon direction of energy h nu by c, and then this is the transfer direction of the photon is coming in this direction, and the electron and the positron goes off in this direction. Let's say this is electron direction, this is a positron direction. So so this is the direction of positron and electron, and if I draw the component of the momentum, because p and p is the momentum, so this direction, okay, so the momentum along this direction and the momentum along this direction will cancel each other, so the only thing we'll get is in the transverse direction. This is This is P, this is P cos theta, and this will be P sin theta, and this is minus P sin theta. So this will be P sin theta, and this will be minus P sin theta. So P sin theta minus P sin theta will cancel out. So we're going to have P cos theta and P cos theta. So from the conservation of energy, what uh, we know that this is the h nu is the energy with which this photon is coming. The photon is coming with energy h nu, and uh, because gamma mc square is the total energy of each momentum member of the electron positron pair. Okay, so this is twice gamma mc square. So h nu is the photon energy, and gamma mc square is the total energy of electron positron pair. Okay, so electrons energy is gamma mc square and positron energy is gamma mc square, so that's why it is 2 gamma mc square. So energy conservation does require that in the initial we have a photon energy h nu square, and the energy in the final state, this is gamma mc square, twice gamma mc square, the energy of the electron and the photon. Okay, fine. So figure 2.6 2.6 is a vector diagram of the linear momentum of the photon, electron, and the positron. The angle theta are equal in order that the momentum be conserved in the transverse direction, and in the direction of the motion of the photon, for momentum to be conserved, it must be true that what it must be true that h nu by c will be 2 p cos theta, because this photon is coming, which this is h nu energy, and the momentum will be h nu by c. Okay, this is energy and this is momentum of the photon, and this is direction of the photon. This is cancel out, and this direction, this is like this is theta, this is theta, this is p cos theta, and this is p cos theta. Okay, so this is p sine theta, and this is minus p sine theta. These will cancel out, so we are going to sum this two transverse components. So this is 2 p cos theta, momentum in the direction of, and the initial momentum is h nu by c. So we can see that h nu by c is twice pc cos theta. So when p equal to gamma mv, relativistic momentum, because normally what you see is p is linear momentum and is mv, but relativistically we write gamma times mv. Okay, and gamma here is what? Gamma is 1 under root 1 minus v square by c square. You know this, and this is for electron as well as for positron. So we said this equation becomes h nu is in place of p, we write gamma mv. So this is gamma m, and v comes here, and we multiply and divide by c, so c is there and c square is there, and then cos theta remains same. Okay, so this h nu is, we put in place of p is gamma mv, and multiplied by c and divide by c, so this expression becomes this expression. Now what we can see that, so from the conservation of energy, as you have seen that conservation of energy demands that h nu should be twice gamma mc square, as you have seen from the previous slides. See, if I put this h nu in this reaction twice gamma mc square, is twice gamma mc square, and then v by c and cos theta. So this will cancel out. So this equation demands that 1 equal to v by c and cos theta. So this equation to be true, we need that v by c multiplied by cos theta must comes out to be 1. But whether it is true or not, can cos theta be 1? For cos theta to be 1, uh, theta has to be 0. Okay, and if theta is 0, that means these two particles, if theta is 0, so these two particles are going in a single line. So electron and the positron are going in a single line without any angle. So it is not possible, because these two, this is a particle and this is an antiparticle. If they are going with an angle 0, because so this is a matter and this is antimatter, they will annihilate each other and becomes an energy. So the particle antiparticle, if we come close to each other at 0 angle, they will annihilate each other, and then matter becomes the energy. So it's not possible to these two particles to go in the same direction with an angle 0. So certainly they are going to have a certain angle theta. So the cos theta is not going to be 1, it has to be less than or equal to 1. Okay, and what about v by c? So this also cannot be 1, because for v by c has to be 1, then v has to be equal to c, and v cannot equal to c, because when v equal to c, relativity tells that when something moves with the velocity of light, its mass tends to infinity. Okay, because so when v is equal to c, its mass tends to infinity, which is almost unphysical. So if v is not equal to c, then v by c is also not going to be equal to 1. It has to be less than 1, and v also cannot greater than less than c. So both the factors which are in this bracket are not going to be equal to 1. They are always going to be less than 1. So if both these quantities, this and this, are less than 1, then this side is not going to be equal to 1. So this is not going to be equal to 1. Fine. So that means all this process in which the conservation of energy and the conservation of momentum we are applying, it's not finally giving us a correct result. So you can see that in driving these, we have not considered uh, the presence of the nucleus, in the vicinity of the photon. We have not considered the energy and the momentum of this nucleus. So we have supposed that there is nothing is present there. The space is empty and the photon is coming out and it being materialized into an electron and a positron. So what we are getting is not the correct mathematical statement. So that is why uh, it is impossible for a pure production to conserve both an energy momentum unless some other object is involved in the process to carry away part of its initial momentum. And that is why we need this nucleus. So that because the nucleus is very heavy, so the part of the momentum is carried away by the nucleus, and we also know that the some very few amount of energy is also being taken away by this nucleus. So the main thing is that the momentum part, which is taken away by this nucleus, which is responsible to correct this energy and momentum conservation relation. So that's why the simple mathematics proves that it's almost impossible for pair production to conserve both energy and momentum when it is occurring in a free space. So there has to be some nucleus. So when a photon is passing through in the vicinity of the nucleus, then only it can materialize into an electron and a positron, and that photon must have an energy of 1.02 MeV least and 1.2 picometer of wavelength to have the phenomena of pair production. Fine.